Hello everyone, can you see me? If you see me, just write in the chat box so that I know that I'm live and I'm audible. Just waiting for signal from someone that yes, I'm live. Yes. Okay, there is some yes Chopra saying yellow sir. So yes, you can hear me. I'm audible, perfectly visible. Disha, Devraj, a third. Good. Welcome to you all. Okay, so this is your educator Alok Kumar, and today I am going to cover some interesting cyclic identities, which is normally not covered in high school, not at all. But very wonderful topic. Before I begin, let me do a quick survey of the promotions available, and then we will be good. So let me just go to the documents and show you something. So you have got Unacademy Super 20 now. You might have seen the promos also that I made for this, the shorts, and then you can also be one of the top 100 rankers, and then you can stand a chance to attend a 2-day in-person all expenses paid boot camp. Here is the Amay Singhal, like who really was like a Unacademy student, and then he did really well. Then next you will have some other things, features like same thing, that dates are there, practice test, and then that 3 subject slots are there. You can check that. Lot of scholarships, then combat, and then you have your race towards J22 top ranks. So just take the test and do all the thing. And brand new updates, don't miss these updates on the Unacademy Ask a Doubt. That's all from now. That's all for now. And then let me now show something, the people who might have joined us today and not before. So a word about me. So let me check in the, okay, so you can Google later on, but this is a brief introduction of mine. So I'm Alok Kumar, and I teach mathematics live on Unacademy for both ITG Advanced and also for Olympiad. And you can see my credentials. You can check it later. And similarly, you can enjoy AHA lectures by me. I'm a big fan of maths, right? And these are my classes going on. Some classes are going on, some are still scheduled. So that's all. Let me begin the lesson for today. So today we are doing this cyclic identities. So the topic is that from charming cyclic identities to a challenging USAMO problem. It indeed is. The topic is really challenging, really. I just love these identities because they crop out of nowhere sometime, and it really happens that sometimes they are a hint to a difficult problem. So let me cover the basics first, and then we'll go to the other things. So let me add some pages and let me introduce you to this one. You will also see some recurrence relation, some Newton sums, lot of wonderful things. It's a heady cocktail of lot of lovely maths. It is one addiction worth having. Okay, so first let me have some humble beginnings. So if you think of expression like sigma a to the k and b minus c, these expressions, sigma a to the k, b minus c. Okay, if this is there, then for k equal to 0 means b minus c. So I'll just say that what is sigma b minus c? It is cyclic, so I'll expand that. That is b minus c plus c minus a plus a minus b, and that is 0. That's a simple 0. If you write sigma a times b minus c, it is cyclic, right? So I am permuting ab minus, it becomes ab minus c plus bc minus a plus ca minus b. So let me write a times b minus c plus b times c minus a plus c times a minus b, and that equals 0. Nothing interesting so far. You are all getting 0, 0, and 0, lot of zeros. But now things get really interesting when you start sigma a squared b minus c. This is your first thing, a squared b minus c. If you expand that, and I will prove it later, that you factorize, you will get negative of a minus b, b minus c, c minus a. Means first time you get some factor, sigma a squared. we'll go further and you get sigma a cubed b minus c, that is negative of a minus b, b minus c, c minus a times a plus b plus c. I mean, this guy is always a factor. This guy is always a factor. A minus b, b minus c, c minus a. Not without reason. When you go the next one up the ladder, I can go on and on, but I'll stop at a to the 4. You are getting negative of a minus b, b minus c, c minus a. And now a to the 4 has come. So what do you expect? What do you expect it to be? Can someone tell? What do you expect it to be? Just think a good pattern. Just like we have been here, good time. So just tell that what you expect here it to be. A minus b, b minus c, c minus a times. Yes, waiting for response from you all. A squared, b squared, c squared, and something else also, right? So it's like a squared plus b squared plus c squared plus ab plus bc plus ca. So I mean, you are getting all things in which you are getting term of quadratic, and then in all the things that a squared type of term means a type of term and a b type of term, right? So a squared terms of type, this is a squared, b squared, c squared, same symbol multiplied with itself, and two different symbols multiplied, so we'll get like this. Just because you got interested, so let me write as a bonus that I did not plan for it, but I'll write a to the 5 b minus c. What do you expect it to be? 5. Negative of a minus b, b minus c, c minus a has to be there. This guy is there, as our experience shows that this guy is somehow being carried. And what do you expect here? Certainly degree 3 term, right? So it will be degree 3 term, right? And it has to be also cyclic. And of course homogeneous, right? Because degree 3 is there. So you will get, you tend to get now a cubed plus b cubed plus c cubed. Means you can get degree 3 terms like same terms, or you can have, so you can make some cube terms, like either you can make power is a itself, or you can make 2 a's and 1 b, this kind of thing, or you can make all different a b c. So a cubed plus b cubed plus c cubed plus a squared b, right, cyclically, plus b squared c plus c squared a, and also the other thing like ab squared plus bc squared plus ca squared, and plus, don't forget this, and plus abc. So you will get this kind of thing. We can prove much more. Yes, but if sigma a squared b is not a good symbol, Devraj, because sigma a squared b means there is no hint of cyclicity, right? Because you will get sigma ab squared also. So you have to write that it permute over all a and b also, right? So I mean that when you write sigma, you have to be careful. Sometimes you write cyclic, sometimes you don't write, when meaning is clear. Here we had both. We have a squared b plus b squared c plus c squared a, this type of term, and then also this one. So in a way you are right also, because you just write that, okay, sigma a squared b, and then so you can write number of terms like 6. Sometimes people write sigma a squared b, then they write 6 terms. That tells you that, okay, we are just counting. That also is a good symbol, but anyway, that's all right. So this is there. Now let me prove this one first. The first thing where things get interesting, and then the second, that's all, and then fourth, of course, we can do similarly. So let me go to the next page. I'm adding a page, allow me to add. Okay, so now it is a cubed, so a squared b minus c, a squared b minus c. This is the first such identity, a squared b minus c plus b squared c minus a plus c squared a minus b. This we are trying to add, this I'm trying to find. So I offer 2 proofs, one, or rather 3 proofs. First proof is that you just replace, remember this one, first proof 1. 3 proofs are there, all are lovely, so try to master all. So first proof is based on the identity that a minus b, sum of these 3 numbers, b minus c plus c minus a equal to 0. So I can replace one of the numbers, say anything, say a minus b or b minus c. So I can replace b minus c as negative of c minus a and negative of a minus b. I can write like this, or any one number. So let me choose this one, a minus b. So I will write a squared b minus c plus b squared c minus a, and here replace a minus b with negative of b minus c, negative of c minus a. So this is negative of c square b minus c, negative of c square c minus a. We have done this. Now once this is done, we can just choose appropriately. So we will combine this one, we'll combine these two, and we'll combine these two. So this is b minus c, so you will get a squared minus c squared times b minus c, and then plus c minus a times b squared minus c squared. I can maintain cyclicity and I can take the common. So I'll take the common b minus c. I want to take b minus c, and then I want to take common c minus a and not a minus c, so c minus a. And so here you will get negative of a plus c, because we have taken this as the common. And here b minus c, c minus a is out, so you'll get plus b minus c, right? C minus a is there, this is c minus a, so you'll get plus b minus c. Just check it first. Let's check here. A squared minus c squared you are getting, so a squared minus c squared b minus c, and plus b squared minus c squared c minus a. So this means we are getting b minus c common, and then we are taking here b minus c, c minus a, so this c minus a, and this is here plus of this is common already. So now we are getting just b plus c. We are just getting b plus c. Minus is gone. So we will get b minus c, c minus a, and c goes out, negative of a and plus b. You can pull out one negative. So negative of a minus b, b minus c, c minus a. Some people may write it like a minus b or b minus c, and they try to change the sign. But I love this one. You also must love this, because actually this is where you see that order is cyclic, and so this is better. Order is cyclic, and so I'm preserving the cyclic order, and so it will be easier. So we'll preserve cyclic order. This is the proof one, first proof. Is it clear? First proof is clear. First proof. Let me go to second proof now. First proof is clear, so second proof, let me go to second proof. So second proof works like this. For second proof, you have got that I will write a squared b minus c, b squared c minus a, plus c squared a minus b. Let me write this as p of a polynomial in a, So these are coefficient just, right? These are just coefficient. So if it's polynomial in a, it means that you will have this. If it is polynomial in a, so think of a as x. Those who have confusion, they can write p of x is x squared b minus c, replace this one, plus b squared c minus x plus c squared x minus b. Just for a moment, because you are used to seeing x, right? So I'm just wrote to give you some familiarity, but actually pa is all right enough. So it's a polynomial in a with b and c regarded as being its coefficients, right? Coefficients, constant, parameters, what you would say. So our hero is a now. So p of a is there. Now use factor theorem. If I evaluate this at b, so if I calculate p of b, it's a polynomial p of b, value of, so a equal to b, p of b, then p of b, if I calculate, I'll get b squared b minus c plus b squared and c minus b. You are just putting a equal to b, and this goes 0, c squared b minus b. So I'm evaluating this polynomial at b. So now if this we evaluate, you check, this is anyway 0, and this sign has turned b minus c, c minus b, so this becomes 0. So p of b is 0. Similarly, you will find p of c also is 0. After all, it is cyclic, right? So p is a polynomial of second degree. It vanishes at b and c both. So I can write p of a as a minus b by factor theorem, and a minus c. And see, don't forget this baby lambda, right? Small baby lambda is also there, lambda, the coefficient lambda. Now this lambda will of course depend upon the constants which are made up of b and c. That is easy to check, because now you see that here b minus c is there, the coefficient of pa, the coefficient quadratic in a, b minus c coefficient is there. So this lambda, if I compare, must be b minus c, and so I can write this is b minus c and times a minus b and times a minus c. I can pull out a negative sign to maintain cyclicity. So a minus b, b minus c, c minus b, and we are good that we got it. So you must love this proof also. This is really wonderful. Using the properties of polynomials, that is one. A third proof is a variation of the same theme. Third proof that goes like this. That's not really the different, but a variation of the same theme. So proof 3 goes like that: P is a polynomial in A. That's all right, fine. So you are saying that A minus B is a factor of this PA. Similarly, B minus C is a factor, and similarly C minus A is a factor. So if at all something is missing, it must be a constant, because you cannot have this degree is just, see, it is A squared B. So this degree is 3 only, no? Like homogeneous of degree 3, right? So we already have degree 3 accounting. So this already, if something is missing, it must be constant lambda. And what we can do that, and this must be A square B minus C. We reason out like this: B square C minus A plus C square A minus B. And to get the lambda, what we can do, we can equate coefficient. So say A square B, this in the expansion A square B coefficient is 1. To get A square B here on the left side, we need to select A from here. We want 2 A's and 1 B. So 1 A from here, 1 A from here, and B from here. But this is 1 A, B, and this sign is negative, right? So you will get negative A square B. That means that this lambda implies that lambda must be negative 1. And so we are again good that we got that this number, that this expression sigma A square B minus C is negative of A minus B, B minus C, C minus A. It's lovely to talk about it. You just can't help to fall in love with these kind of expressions. So this is your thing, that you got A square B minus C, B square C minus A, C square A minus B. Similarly, you can do A cubed also. So let me just get you started at least. So other things, the other result, the other proof, other thing will be this one, that I will get A cubed. So I'll get sigma A cubed B minus C. First timers, it is recommended that you will have to write it in a developed form. So you expand it: A cubed B minus C plus B cubed C minus A. That's really nice. B cubed C minus A plus C cubed A minus B. So you have got this kind of thing. We again want to do the same stuff, and we want to find. Although we can have many other things also. And first of all, that I told you that why it has always factor, that is clear now, right? Because if I write P of A as again A cubed B minus C and plus B cubed C minus A and plus C cubed A minus B as a polynomial in A, so P at B is 0, and again P at C 0, just like the last time, right? So P of A and P of B and P of C is 0, and so A minus B, A minus C is a factor. So A minus B, A minus C is a factor. And if I look at a polynomial in B or C, then again you will find that B minus C also is a factor. And that is why you have always, in all these numbers, in all these things, you have this negative A minus B, B minus C, and C minus A, making its appearance everywhere in all of them. That's also a good point. So this is clear here, okay? And but then it is much more than this, right? So as I told you, as I wrote on the first page itself about, I listed it A cubed. These are the things getting interesting. A cubed, I wrote like this: A plus B plus C. A4 is like this. This again you can derive similarly. So I'll just get you started. So now we can again write A minus B. We can again write A minus B as negative of B minus C minus C minus A. And so A cubed B minus C plus B cubed C minus A plus C cubed A minus B. This rewrites itself as A cubed B minus C plus B cubed C minus A and minus C cubed B minus C minus C cubed C minus A. Again you can combine B minus C with this one, and then you can also combine this B cubed C minus A with this one. They are the natural partners. Once you combine them, then let's see what you get. You're getting B minus C times A cubed minus C cubed, and then you are also getting here plus C minus A common, and you are getting B cubed minus C cubed. I can write negative throughout, negative I can take throughout, and then I'll take the common B minus C and c minus a, and so this negative is common here, so this is c minus a, and this is all right. So I can take here, this is not a stell, right? So this is, so I will write rather this one, b minus c minus a I took, and here this is negative, and I'll write here a square plus ac plus c square. This negative comes because this was c minus a, right? So this is this, and c minus a, so I will get here b square plus bc plus c squared. Again, you see c square will cancel. That's a good sign. And then you will get b square minus a square. So let me write here only, just shift the page and I will use this page. And so you have got b minus c times c minus a, and times, this is negative a squared, negative ac, and plus b square and plus bc. I will focus here only. So this is a square minus b square. I can write negative of a minus b, a plus b, and this is, I can write as, this is a minus b, so I can write here negative of c and a minus b. So you can write it is a minus b and a plus b plus c, all negative, and this negative will go out ultimately, and so I will get again the same good result, that negative of a minus b, b minus c, c minus a, and times a plus b plus c. So things are getting really interesting. Now you are getting a plus b plus c. I hope it is clear till here. Any doubts you can ask if there are any doubts. I just give you some time to just soak it all in and enjoy the beauty of all of it. Okay, so let me go to the first page and show you that what we really achieved till now. So I started with very simple things. So b minus c, that is 0. First two were 0. The other one, a squared, a cube, this is where things started to get interesting. And this is negative of a minus b, b minus c, c minus a, which will run throughout all the expressions like this. And you are getting here a plus b plus c here. You are getting here a squared plus b squared plus c squared plus ab plus bc plus ca, and you are getting here a cubed plus b cubed plus c cubed plus a squared b plus b squared c plus c squared a plus ab squared plus bc squared plus c squared, and plus abc. This all term you get a to the power 5. So I derived a square a cubed. You also can derive a to the power 4, but better would be that after this we will do what we say is that we'll do something called recurrence, right? So that will be clear in the next page. Let me show you how I'll get this recurrence. So first let me introduce in the form of a problem, that this problem, a to the k by a minus b minus c, this also occurs quite often, is sk. So I'm writing this as sk, and we want to prove that s0 is s1 is 0, s0 s1 0. So we want to prove that s0 s1 this all are 0, and we want to also prove that this s2 is 1, s3 is a plus b plus c, and s4 s5. So you see, this is almost the same thing. Till s3 we have done, s4 we have not done. So you will see how to do it. I'll give a new proof called recurrence relation. So let me turn the page in, or first let me start something here. Okay, see, we know that ABC, this method is similar to the thing we employ while deriving Newton's sums, right? Newton's sum. So that is another interesting topic. I will make a video on this also soon. Now ABC. So ABC are the roots of x cubed minus a plus b plus c x squared minus ab plus bc plus cax minus abc is 0. These are the roots of this one, x cubed. So I can also write that I can multiply this by anything I want. I multiply by x to the power m minus 3. So I will write here x to the m minus a plus b plus c x to the m minus 1. Power decreases by 1 because original difference also was 1. ab bc ca x to the m minus 2, and minus abc times x to the m minus 3 equals 0. So a, b, c all are roots of this equation. They were of this also, but they satisfy this also. And let's agree to put a good symbol. A plus B plus C is sigma 1, as we say, symmetric function of 3 variable. A, B, B, C, C, A is sigma 2, and A, B, C is sigma 3. We put like this, sigma 1, sigma 2, sigma 3. So A is root of this one. So I can write A to the power M minus this, minus this. So I can go to the next page, and I can write, so I can write like this. So I can write A satisfies A to the power M minus sigma 1. If you think it is sigma 1, you can check sigma 1. I'll write sigma 1. And A to the M minus 1 plus sigma 2 A to the M minus 2 plus negative sigma 3. So alternate negative positive. Negative sigma 3 A to the M minus 3 equal to 0, because you cannot go more than sigma 3, right? So this is what we get, sigma 3. Now, same for BM also, same, and CM also. What I do, that I divide this by A to the power M, I divide by A minus B, A minus C, plus minus sigma 1, A to the M minus 1 over A minus B, A minus C, plus sigma 2, A to the M minus 2 over A minus B, A minus C, and negative sigma 3, negative sigma 3, A to the M minus 3 over A minus B, A minus C equal to 0. This is what I'm getting. So this is what we get, A to the power M minus this one is 0. Because B and C also satisfy the same thing, B and C, they also do the same thing, B and C. And so I can write for B, I could have written similarly B to the M over B minus A, B minus C minus sigma 1, B to the M minus 1 over B minus A, B minus C, B minus A, B minus C, plus sigma 2 B to the M minus 2 over B minus A, B minus C minus sigma 3 B to the M minus 3 over B minus A, B minus C equals 0. And similarly for C also I can write, right? So let me write, because I've written already. So C to the power M over C minus A, C minus B. When you become fast, what you can do, you can write just sigma. So this is C minus A, C minus B plus sigma 2 C to the power M minus 2 over C minus A, C minus B minus sigma 3 minus sigma 3 C to the power M minus 3 over C minus A, C minus B equal to 0. I can add these three, all three I can add. I can add all of them. So what is the first term you get? You get A to the M plus B to the power M plus C to the power M, right? This you get. Are you getting my idea? So let's check that what it was. So if you see this way, see A to the M over this, B to the M, or this, like this. So you will get like A to the M over A minus B, A minus C, plus B to the M over B minus A, B minus C, plus C to the M over C minus A, C minus B, minus, this minus sigma 1, and you will again get here, this is A to the M minus 1, same thing, over A minus B, A minus C, and similar two more terms, and then plus sigma 2, and then minus sigma 3. I hope by writing this long thing now it is clear that what is coming. It is actually good to feel quite easily, but then I just wrote it out expressly for you, so it is easy for you to understand all the things. So we have reached till here. This is our main expression. This is because this is what SM was. SM. So I can write, or SK or SM. So I can write SM. So I can write S of M minus sigma 1 SM minus 1 plus sigma 2 SM minus 2 minus sigma 3 equal to 0, minus sigma 3 SM minus 3 minus sigma 3 SM minus 3 equal to 0, and I can write M greater than equal to 3, M greater than equal to 3, because from 3 only we started the things, right? So M greater than equal to 3. We cannot go to 2 or something. 3 means that we did not multiply, right? We multiplied something. So 3 is this, m minus 3. Now, if this is the thing, then I'll go to the next page and I'll write. So you have got S of m is sigma 1 Sm minus 1 minus sigma 2 Sm minus 2 plus sigma 3 Sm minus 3 m greater than or equal to 3. So if you want sigma S3, if you want S3, and by the way, what happened to S0, S1, S2? So S0, S1, S2, they are computed. They are computed by hand. I mean that you just have to put the values that we have done the work. For example, if you think of S0, what was S0? S0 was 1 by a minus b, a minus c, 1 by b minus a, b minus c, subtract from b the other symbols, plus 1 by c minus a, c minus b. So it is a minus b, b minus c, c minus a, c minus a. This is negative, and you will get here b minus c plus c minus a plus a minus b. That will be 0. So you got this as 0, S0 as 0. If you come to S1, so it is a over a minus b, a minus c, again b over b minus a, b minus c, plus c over c minus a, c minus b. This time, again you can take common, that is a minus b, b minus c, c minus a. You can take like this. And then you will get here a times b minus c plus b times c minus a plus c times a minus b, and that will be again 0. So it is 0. However, if we take S2, if you take S2, then S2 will become a square over a minus b, a minus c, plus b square by b minus a, b minus c, plus c square by c minus a, c minus b. Now if you take common, then you will get negative of, you compute that, it is a minus b, b minus c, c minus a, and you are getting here a square times b minus c. Just check it, because you already got, this is a minus b, a minus c, so a minus b, a minus c, so this negative is there, so you will get now b minus c. Otherwise you have got c minus b. A square b minus c, b square c minus a, plus c square a minus b. And we know that this number, this expression is negative of this one, and so we get just 1. If a, b, c are all different, of course, for this to happen, so this we got 1. So we got S0, S1 0, and S2 is 1. So this recurrence, for this recurrence, I am getting S0 is 0, S1 is 0, and S2 is 1. S2 is the first major thing, 1. S2 is 1. So let me calculate S3 using that, S3. So Sm I will have to write on the next page again. So Sm, I am getting Sm as sigma 1 Sm minus 1 minus sigma 2 Sm minus 2 plus sigma 3 Sm minus 3, with S0 is 0, S1 is 0, and S2 is 1. So that's good news. We know 3 initial values. So I can put, this was m greater than or equal to 3. So set m equal to 3. So I can just write that set m equal to 3 in the recurrence. M equal to 3. To get S3, it's sigma 1 S2 minus sigma 2 S1 plus sigma 3 S0. Now sigma 1 is a plus b plus c. S2 of course is 1, others are 0. So I got a plus b plus c. So we got this in a clever way. Sigma 3 is a plus b plus c. Sigma 3. So this is S3. Now if I want to get S4, that we calculate S4. So S4 becomes sigma 1 S3 minus sigma 2 x2 plus sigma 3 S1. So I can write S4 as sigma 1 S3. So sigma 1 is sigma only. So a plus b plus c, and times S3 we got a plus b plus c minus sigma 2 S2. Sigma 2 S2. So now S2, what is S2? S2 we got, right? S0, S1, S2 is 1. So sigma 2 is AB plus BC plus CA, and then this is 1, and this is sigma 3, and times this is 0. S1 is 0. So I am getting A plus B plus C whole square minus AB plus BC plus CA. So we are getting A square, B square, C square, and plus 2AB. So we are getting only plus AB plus BC plus CA. Correct? So this is what we got. So we got it very beautifully now using recurrence relation. There we just calculated, hand computed. We hand computed. So we got this one. Is that clear now? Till S4 we got. Similarly, we can get S5 also, because the problem says to calculate all these things. So I'll show you that what they do. They tell you to calculate S0, S1, S2, that you can do by hand, S3 by recurrence, S4 by recurrence, and S5 also by recurrence. So we got this one. In any doubt here, any doubt that you are having, then you can just ask before I move on. Yes guys, any doubt if you can have, you can just ask me before I move on. Okay, so I take it that this is all right. So this is a tough problem that we did. One more was this, a to the k over a minus b, a minus c minus d. It is same question, but 4 different symbols, right? Now we have got 4 symbols. We have got symbols a, b, c, d. Earlier symbol was just a, b, and c. So 4 symbol, obviously, then sigma 1 all will change here, right? So our relation will be like this here, that see, we have got a to the a, b, c, d all will satisfy. They all satisfy x to the 4 minus sigma 1 x to the cube plus sigma 2 x square minus sigma 1 x, sigma 3x plus sigma 4 is 0. If you talk of a, it satisfies a to the 4 minus sigma 1, and this is a cubed. So I can write, instead of this I can just multiply by m. So I would multiply by m, that will be better, because directly I will get. So x to the power m minus sigma 1 x to the power, this is multiplied by m minus 4, so m minus 3 plus sigma 2 x to the power m minus 2 minus sigma 3 x to the power m minus 3 and plus sigma 4 x to the power m minus 4 equal to 0. So we got like this, m minus 4, this one. So I can say that the recurrence in this case for these numbers will be, name is still s, so I'll get s of m minus sigma 1 s of m minus 1 plus sigma 2 s of m minus 2 minus sigma 3 s of m minus 3 plus sigma 4 s of m minus 4 equal to 0. We get like that, sigma 4 s of minus 4. Now I can write Sm in this form, Sm. So I can write Sm as, so I can write s of m at sigma 1 Sm minus 1 minus sigma 2 Sm minus 2 plus sigma 3 Sm minus 3 minus sigma 4 Sm minus 4, m greater than or equal to 4. I can use this result, and from this I can again derive all those things, because I know for this one, but I'll have to hand compute for other numbers. So again we will get the same kind of result. You can see here that here S0, S1, S2 is 0, means first symbol, there are 4 symbols, so till S0, S1, S2, this is all 0, and S3 is 1, and S4 is the all of sigma, so that we can quickly write. So this is clear, that yes, this is clear. This is little involved than that one, but again this process is same, exactly the same process, just applied to 4 variables. I will do more applications of it rather than the theorem itself that I already did. Okay, anyone having trouble with recurrence relation? Those who are seeing for the first time, maybe. So you're just deriving it each step so that you do not make any mistake. Okay guys, so let me go forward and do some interesting applications, very interesting. Yes, first is this one, a square, and this one, a square times exponential. This is actually we can do in 2 different ways. This is comes from polynomial also easily. Okay, but let me do the way I have done right now. Two methods held. So this is method 1. So solution will be like this, that I take the LCM, that is in cyclic form, a minus b, b minus c, c minus a. Then negative will come here. So I'm ready with this, that okay, this negative is there. Now a squared, so you will get here a squared x minus b, x minus c, and times you will get b minus c, right? Because that is what will come here, b minus c. Then plus b square, write one more term, x minus c, x minus a, and you get c minus a. And similarly the third term will get. Let me try to simplify the first one only, the first command, this one. If this is something good, we can go along. So a square x minus b, x minus c, b minus c. That will be a square x square minus b plus cx plus bc, b minus c. Like that we are writing. So now check this. If you multiply, you will get x square times a square b minus c minus a square b square minus c square x. You will get plus abc a times b minus c. You will get like this, right? So result is sigma. Your result is sigma, because if you write sigma over this one numerator, the numerator you will write negative already is there, so that you leave. So that is sigma of, and you are getting this one. So sigma of x square is out, a square times b minus c, minus sigma is out x, and this is a square times b square minus c square, and plus abc is out, sigma a times b minus c. We know this is 0. We know that this goes to 0. So we know that this goes to 0. So this goes to 0. And we know that this number also goes to 0, because these are cyclic applied to a square, b square, c square. So the only task is here, a square. And this is no stranger, because now we know the value. So we know that this whole stuff, this thing is x square and times negative of a minus b, b minus c, c minus a, which is the denominator, and negative already is there. So it means I will get this, after all cancellation, I'll get just x square. I'll just get x square, and that is what we proved, that we are getting x square. So we got x square here. So that is the first proof. That is the using power of cyclic identities. I'll also do the second proof. So let me run a second proof. That might be little better here, and it tells you about the power of binomial. So imagine, so these are called coefficients, right? These are all coefficient. So what you do, that you tell, so let me add on the next page. So a square, you want to prove a square x minus b, x minus c over a minus b, a minus c plus b square. So a square plus b square, and x minus c, x minus a, x minus c, x minus a upon b minus c, b minus a plus c square times x minus a, x minus b upon c minus a, c minus b. This is your left hand side, and right side is x square. You want to prove x square. Right side is x square, x square. So you take, you consider this as px. So you call this as p of x, polynomial p of x, and you call this as q of x. So apply this. If you call like this one px qx, then you are saying that okay, degree of p is 2, degree of q also is 2. So degree of p is 2. Degree of p is 2. Right now degree of p is 2. But what is happening? That if you write p of a, p of a, p of a, then p at a, these all things go 0. This is a factor, a factor. P of a is, here you put p of a is just a square by design. P of b is b square, and p of c is c square. So it means two polynomials px and qx, and qx is x square. So q of a is a square. It's a good theorem. Q of b is b square, and q of c is c square. It means two polynomials p and q of degree 2, at most I will say, because that may vanish also. So let's say that two polynomials of degree at most 2, they agree on 3 different points. So two polynomials of degree at most 2 agree on 3 different points, right? At least 3 different points. So it is more than that, right? So it means that these two polynomials must be identical, or they must agree for each value of x. That's the meaning. I repeat, here I am saying that if two polynomials p and q, px and qx, q is certainly degree 1, degree 2, q will depend upon coefficient, but at most 2 I will say the word. So if two polynomials p and q of degree at most 2, if they agree on 3 different values, degree plus 1, 3 different values of the variable, it means that p and q are identically equal. They agree for all values. So that is first proof. Second proof, and third is a variation of the same theme. Third I can say that construct a polynomial Rx is px minus qx. So construct this polynomial. So everything is this side, on the left side. So now if you construct like this, you will get r of a equal to 0, r of b equal to 0, r of c equal to 0. So right now I'm saying that r is, if it is degree to degree 2, so I'm saying that the polynomial Rx is of degree at most 2, and it vanishes for 3 different points, a, b and c. It means Rx must be the 0 polynomial. Rx is 0 polynomial, that is px equal to qx. So they are equal. That's also good. That Rx must be. Okay, so I will avoid red. Arpit. So this is clearly visible, or not clearly visible. Okay, so what is clearly visible, Arpit? Which one should I use more often? Blue or green? Which one should be viewed more often? You are for blue or for red? Blue or green, because red anyway you are not saying not much visible. Okay, so argument is clear, that this argument was based on the fact that this Rx, a polynomial of degree at most 2, it vanishes, it is 0, it vanishes, and 3 distinct points, and so it must be the 0 polynomial, meaning that Rx is identically 0. That means that px square is qx, px is qx. That means px is qx, and so we are done. Okay. Next is also the same variety, x minus b, x minus c minus c, this one. So I can construct like this. So either I can do through proof 1 is through this one only. Proof 1 is through cyclic identities. So I can clearly write again, I can expand. I can write x square, x minus b, x minus c, I can write x square minus b plus c, and then plus bc. I can have another thing also. Let me tell you that other thing also if I find time. So this is this one, green. Okay, so minus b plus c bc. Here it is, alright, b plus c bc, this one, and upon a minus b, a minus c, and so on. So I can write this as this numerator as, so I can write this numerator as negative of, negative will be throughout coming. So negative I can just leave right now. So, or let's write this way, that I can write this as negative of, and a minus b, b minus c, c minus a, and here you'll get x square minus b plus cx plus bc, and times b minus c, right? If you follow, you will get like this, b minus c. Okay, so negative I will just leave. So you will break it up, you'll get x square times b minus c minus x times b square minus c square, and plus bc b minus c. You see, this is 0, this is again 0, this is again 0, because you are getting x square. If you do sigma, so sigma x square b minus c, x square will come out, it is sigma b minus c, it is 0. Similarly, this also is 0. Remaining is just this only. So sigma BC B minus C. But this we know. This we know. This had some relation to A square B minus C. Why? Because we can write like this one. See, BC B minus C plus CA C minus A plus AB A minus B. This equals. Now collect terms of A and B. So this is AB A minus B, right? So I can write here this is A square B and this is A square C. So this is negative of A square C and plus A square B. So this is negative of A square B minus C sigma. This is like this, negative of this. That we already know, right? And so this whole thing is now A minus B, because negative will come B minus C, C minus A. So BC B minus C is this only. So BC minus C is this. So we'll get here, this only will get, and this is, so this term only will contribute, and this term will give you A minus B, B minus C, C minus A, C minus A, and upon A minus B, B minus C, C minus A, this one. And so this we will get again as 1. So this is just this one. Okay, this is this way. Okay, one more thing can be using polynomial again. So let me finish it here only. So for polynomial we can do like this. That is a polynomial px. I'll write this as px minus 1 is qx. So px minus 1, it's a polynomial of degree at most 2. Degree at most 2, because we do not know something will be 0 also. So degree is at most 2. So if degree is at most 2, and then we clearly see that it vanishes at 3 different points. QA is 0, QB is 0, and QC 0 is distinct. It means it must vanish identically. That is, in fact, PS is identical to N. So Px is 1 for all x, such that this may not happen. Like that. So we got this. Okay, alright. So far so good. Let me go to the more challenging stuff. We will slowly build the momentum for our USAMO problem. So we are getting here. Let me check that have we missed something, or we have not missed. We have not missed. So we'll go this one. This is a classic problem. Is red visible on the white background? On black it is not good, red maybe, but then on white it is good. I can at least see it, but you tell me that on white, is the red background good? In the white background, red is okay? So alright. Okay, so this problem we'll do like this. That I'll take both separately P and Q. So our P is A minus B by C plus B minus C by A plus C minus A by B. So this is common A, B, C. You are getting A, B, A minus B, B, C, B minus C, plus C, A, C minus A. So you are getting now, you see this is A, B minus B we just did right now. That we are getting, this is just A minus B, B minus C minus A. No negative sign, right? And that's what we're, just check it. We got A square B minus C plus B square C minus A plus C square A minus B, like this. C square A minus B. Now this is of course A square B and minus B square, so it's alright. You are getting AB minus B, so this is same thing. Negative also will come. So AB A minus B. So AB minus B, this is negative of A minus B, B minus C, C minus A over ABC. This is PQ is simple. PQ we get using our identity. Q is this much. So Q I have to simplify a little. Q is C by A minus B plus A by B minus C plus B by C minus A. So you will get here A minus B, B minus C, C minus A and times, you will get here C times B minus C, C minus A plus A times A minus B, C minus A, and plus B times A minus B, B minus C. So the best part is that I can do sigma for it, sigma. So I want to write this one. That what is this? Means I want to plan this C times B minus C, C minus A. What is this? C times. If I know, then we can do other thing. So how do you expand? How do you expand sigma C times B minus C, C minus A? So I first take out a negative sign. I write sigma C, and this is C minus C minus A and C minus B, B minus C minus A, right? This is B minus C, C minus A. So around C I will do around C. So this is C times. This is minus C times. This is C square minus A plus BC plus BC. And negative has come out before only. Negative. Yes, like that. C B minus C. So I'm just writing like that. C minus C, C minus A, and then there is no negative here right now. So we'll just write this one, sigma C, C minus A. Now this is sigma C. This is sigma C, and C square minus A plus BC plus BC. Now I know that A plus B plus C is 0. So this becomes 2C square plus BC, because A plus B plus C happens to be 0. So I write like this. Now this becomes sigma 2C cubed plus sigma, and this becomes CBC. So C square B. So what do you get? No, this is your AB. This is your AB actually. This is your AB. This is your AB actually. This just check. This is your AB. So symmetry is there, ABC. So you get this one and sigma CAB. So that is 3 just, right? This one, ABC. And what about some other thing? Any other thing that we can think of? A plus B, C, 2C square plus AB. Is it okay that someone is getting the answer? C square plus AB. So now it is easy, because now we can use that this is 2C cubed. This is 2C cubed. 2C cubed and ABC. So now we know that A cube, B cube, C cube is 3ABC, right? We know that's A cube, B cube, C cube. We know that sigma A cube is, or A cube is 3ABC if A plus is 0. So that becomes 6ABC and 3ABC. So that becomes 9ABC. So that's 9ABC. So we get here 9ABC. You check here now. We get here 9ABC. We get A minus B, minus C, C minus A, and we get here ABC. So it means when you multiply all of them, things will cancel. We'll get only 9. We'll get only 9, because this we have reduced to this point, right? And this we have reduced separately, but then by opening the bracket in a good manner. So that both will get. So this is what we'll get for this one. And any question? Any question now? Some new learners have come up. Any question like Manisha or I see like Devasish, Karmakar, or other people? Any question do you have? We have covered some ground, and then we are doing some interesting identities. So if you have any questions, you can just ask if any step is not clear. This is a classic problem. 9. This is a good question. Okay, now let me do this. Is a tricky problem. This is very tricky. This is really tricky. Because now this is not happening. This is not happening on ABC, right? 4 symbols are there first of all, and then you don't know that what is happening. So first, let me play with the first term. Rearrange. A square, B square, C square. Just tweak a bit. A minus D. Touch it up. C minus D. In fact, the form of answer also tells me something, but this might not be given always. So what do you think we can do here? Any idea what we can do here? Before I tell the solution, can someone just tell that what he can do? A square b square c square upon a minus d times b minus d times c minus d. Yes, what we can do? This is really tricky. Things get tricky here. It can be easily given, and ABC will be some numbers, and you will be finding the answer. So what I do, I write it like this. I write this as a square b square c square as. See, this form also tell me something, that I need not work with ABCD. Rather, I need to work with ABC, ACD, ADB, and BCD. So that's the thing that I want to work with this one. But let me just write this way, that this is a squared, b squared, c squared. Okay. Here this AD is there, no AD. I will write here, this is, I will write BCA. So I will write BC A minus D times, this is again AC B minus D, and times AB C minus D. So I multiplied like this. BC, I multiplied BC, AC, AB. So I must multiply numerator as well. So BC, AC, AB. So that gives me a to the 4. So ABC to the 4. Okay, this we are getting A4, E4, C4. You can check that we are getting this. And upon what we are getting. Can someone tell that what he is getting now after this? After this you are getting just BCA. Let us do this way. You are getting ABC minus BCD, again ABC minus ACD, and again ABC minus ABD. We are getting like this one, first term. So this tells you something. What? That if I take ABC is alpha, ABD is beta, ACD is gamma, and BCD is delta. If I write this alpha, beta, gamma, delta, then this expression becomes alpha to the 4 upon alpha minus beta, alpha minus gamma, alpha minus delta, right? This is there, alpha minus beta, gamma, and delta. So it is sigma squared. Correct? So what you will do is this way, that we will write now alpha to the 4. So let me go to the next page, add the page. So we are getting now, this is a tricky problem, so please understand clearly. So now we are getting alpha to the 4 by alpha minus beta, alpha minus gamma, alpha minus delta, plus beta to the 4 over beta minus alpha, beta minus gamma, and beta minus delta, then gamma to the 4 upon this one. So there are 3 things. So this is gamma minus, you can check that there are 4 terms. See, you can check that there are indeed 4 terms. So you'll do like this. So gamma 4 over gamma minus alpha, gamma minus beta, and gamma minus delta, and last term will be delta to the 4 over delta minus alpha, delta minus beta, delta minus gamma, and so on. So now these four things, no? Now you know that this is your S4, right? And this was nothing but alpha plus beta plus gamma plus delta there. And so alpha, beta, gamma, delta. So your answer for this question would be, because it is ABC, so we'll get here ABC plus ABD plus ACD and plus BCD. So we'll get these 4 as the answer. So this is the thing to be done. Okay, let's check it. This is a tough problem indeed. Any day it's tougher. This can be asked in identity, so this is the way to it. So I look closely that I multiplied and then I got all of them. Yes, any doubt here in this question or any previous question, something? Okay, let me go to the next one. Now this one, you have to simplify this expression. This looks just out of place. I'll tell you a lemma. You can use that lemma to prove this. Let me tell some lovely lemma which we can easily prove, and we'll get that. So let's see that what this means. What abx minus y square plus bc y minus g square plus ca g minus x whole square. How does it expand? What is the expansion of it? That you have to see. This expansion. So let me expand. This is ab x square plus y square minus 2xy y square minus 2yg plus g square plus ca. We'll write g square. So plus ca times bbc plus ca times plus ca times plus ca times g square plus x square minus 2gx. This one, ab. So now what we can do? Can you understand that what is going on, or what we can do? What we can do here to reduce it or to factorize it in some other form, or write it, or just write it different. Write it little differently. What we can do? abx minus y square plus this one. And see, it is given ax plus b plus c is 0. That you check. This is given. This is given. So if this is given, I can make use of that, right? So I can make use of that in different manner. What I can do is that already it is given abx square plus y square, right? And ax square. So suppose, so this is one thing. Suppose you compare like this. Suppose I give you another expression. Let's check that how it matches. Suppose I give you expression a plus b plus c, ax square plus by square plus cg square, this one, and minus ax plus by plus cg whole squared. Suppose I give you this expression. How will this expression match? This one. There is matches here. Does it do or something? Ax by cg. Let me multiply this. Let me see this one. That's what it gives you. So if you expand it, you will get a square x square plus aby square plus acg square plus, now a is gone, from b, bx square b square y square plus bcg square plus, from c, cax squared plus cby square plus c square g square, this one. And then minus, you have to do minus. So a lot of things are minus, right? ax by cg. So I can write this as a square x square plus b square y square plus c square g square plus 2abxy 2bcyg plus 2cxy, this one. Now see, if you see, this is cancelling, no? See, 2abxy, these terms are there, only this is not there, abx square. But don't worry, this is already multiplied. So see, abx square, so aby square is there, right? So we want to get ab x square plus y square, and 2abxy is already there, 2abxy. These terms are there, right? And a square x square term will cancel. This will cancelling here. So we'll get the same thing. abx y square and abx square is here. aby square and plus y square. So you can check that aby square also should be there. Yes, ab is x square. So we got that, right? If you got that, then we can combine. It means that these two are equal. So we record in the next page that what we got. It is also a difficult one, a challenging identity. So we got AB, we got this one, AB times x minus y whole square. We got AB times AB times x minus y square plus BC times y minus g square plus CA times g minus x whole square. This one ABCA, that equals your, I just wrote A plus B plus C times AX square plus BY square plus CZ minus AX plus BY plus CG whole square. This is the lemma that will derive this one. Just write this lemma and then derive it once more. That's really interesting lemma. If you do that, you will really be good about it. And now come to the problem. Now it might be easier. Now come to the problem. You will find that given this is 0, this is given 0. So this is 0, then this one becomes, then AB, if this is 0, then AB x minus y whole square plus BC y minus g whole squared plus CA g minus x, AB x minus y, BC y minus g, CA x minus g whole square. Now this number, this is the numerator, and this equals just A plus B plus C and times AX square plus BY square plus CG square, because this is 0, and numerator has got just this one. You can check that numerator has just this one, and so if you divide this, you will get 1 by, so your answer, final answer, you will divide, you will get 1 by A plus B plus C. This, so I can choose ABC in any manner, and I will get again this one. Okay, so this is also one tricky example based on identity. If you don't know, then of course it will be difficult to think about it and do it. Okay. So far so good. Things are clear. Okay. Now see this one, 1 by A minus B minus C. How will you attack this problem, A minus B minus C? It also has got two methods. One method is really quite beautiful, and second I'll do by other thing, like I can do in variables. So A minus B minus C. Anybody wants to add something to it? Okay, the first solution goes like this. Instead of working with symbol ABC, you work with symbol 1 by A, 1 by B, 1 by C. Why so? You will write 1 by A minus B, A minus C. This I can write as A has got some privilege. So you'll get A minus B and you get A minus C. This we have to write in some other manner. So what I will write? I will write 1 by AB, 1 by A, 1 by A, and take AB out from here. Take AB out, that amounts to saying that this is 1 by B minus 1 by A, and take AC out here. That is like saying 1 by C minus 1 by A. Okay, so AB, AC is there, right? So I can write 1 by, this is A square, A cube BC, sorry, 1 by A cubed BC, 1 by A minus 1 by B, 1 by A minus 1 by C. Is the red color okay on white background or not okay on white also? Or white is okay? Is it okay on white or not okay on white? Especially red color. Because it looks to me okay, but I don't know. You are on the other side, so you can tell better. On the black board, I was told that use green one. Okay, so 1 by AQBC. So I will write this as 1 by ABC 1 by ABC, 1 by A squared upon 1 by A minus 1 by B times 1 by A minus 1 by C. This one. So this is 1 by A I can take as X, 1 by B as Y, and 1 by C as X, Y, and G. So I will write this as 1 by ABC, and this is sigma X square by X minus Y, X minus G, right? This one. And this I know to be 1, this I know to be 1, this I know to be 1, this whole thing, right? So I know that this is 1 by ABC times 1, and so 1 by ABC will be the answer. So your answer for this question is very good answer. It's just 1 by ABC. You can't guess easily. Okay, thanks Disha for letting me know that red works on the white background. Okay, so this is 1 by ABC. This is one first solution. Second solution is much more interesting, and it's a really different idea. It's just an AHA solution. So let me add the page and I'll show you. So the result is this. We want 1 by A, we want this one, 1 by A minus B, A minus C, 1 by B, B minus A, B minus C, 1 by C, C minus B, like this we want, right? So don't think of three numbers A, B, and C. Don't think of three numbers A, B, C. Don't think of three numbers A, B, and C. Think of four numbers A, B, C, and 0, A, B, C, and 0, A, B, C, and 0. Now that's really interesting. And apply the case for, let me write the case of four numbers. The case of four number was like this: A to the M over A minus B. If you remember, A minus C, A minus D, plus B to the M over B minus A, B to the M on four symbols, B to the M over B minus A, B minus C, B minus D, C to the M, C minus B, C minus D, plus D to the M over D minus A, D minus B, D minus C. This number, this was your SM. This is again your SM. This is SM. If this is your SM, this is your SM. Then for M equal to 0, this answer is 0. M equal to 0, this answer is 0. For M equal to 0, this answer is 0. M equal to 0 means for 1, right? See, I'll have to go much. I'll have to go back like a couple of pages to show you that this was the one of the first examples that we did. See, it is this one we did for this. I did for 3 symbols. For 4, I just told you that how it will come. This is 4, A, B, C, D. So this, you see, S0 is S1. So we are applying S0 case, means we are saying this one. You see, even if D is 0, we are applying, right? D0 does not matter because D to the power K is 0. It is 1, right? So D to the K is 0. Don't forget, even if D is 0, it does not enter into picture. So that's not a problem, even if K is 0. So we are just saying if K is 0, then it does not come only, just 1, 1, 1, all are 1, 1, and 1. So this we are applying. So S0 is 0, S0 is 0, S1 is 0, S2. S0 means this is not present. S1 means they are present. S2 is present. S3 it is 1. Okay, so we are applying this on A, B, C, and D. Yeah, I am applying this on A, B, C, and D. So I wrote like this. So I will apply the symbol A, B, C, 0. Now see what good comes out of it. I'll write A upon A minus B, A minus C, A minus 0, plus B upon subtract all symbol from B, B minus A, B minus C, B minus 0 in the order. Just write in order. C upon C minus A, C minus B, C minus 0, plus, and now 0 upon, but it is 0 only, so just leave 0, just leave 0. So that is, and that was 0, that value is 0. That value, so that value is 1. That value is ABC and 0 upon this one. So A is not, I'll write 1 only. It's not, no need of 1. I'll write 1 only, right? Because no, there is no power. So I can write just 1. So 1 upon. So 1 upon this, 1 upon this, 1 upon this, and 1 again, 1 upon, again 1 upon, again 1 upon, and this time it is 0. So 0 minus A, 0 minus B, 0 minus C, and equal to 0, because this all sum to 0. So from that I'll get 1 upon A minus B, A minus C, 1 upon B, B minus A, B minus C, 1 upon C, C minus A, C minus B. So 1 upon C, 1 upon C, C minus A, C minus B, and here minus 1 upon ABC, because 3 terms, is equal to 0. And so this number, this expression P, that is what we have to find. This P, we have to find P, and so this P indeed equals 1 over ABC, and we are done. So just check this work, that we are getting this one, ABC, 1 over ABC. Is that clear? This is second method, second proof, but this is elegant. This is much elegant, much more elegant than the previous one. Certainly some new idea is there, that don't consider the numbers ABC, expand to 4 variables. The motivation comes from these terms. This A is to be interpreted as A minus 0, B as B minus 0, C as C minus 0. Then you get that, okay, they're actually working on 4 symbols, A, B, C, 0, and so we can get another entity. This is very, proof is also good. Small proof, elegant proof. Okay. Now couple of examples which are really good. So A, B plus C, and this one we want to find, right? So in all of them, first I'll take the common, and so I will write negative of, and this is A minus B, B minus C, C minus C. Will get, this will get always, because A minus B, B minus C, C minus C, and the C, this is not cyclic, so negative will get. And here we are getting A times B plus C times B minus C, B times C plus A, C minus A, plus C times A plus B, A minus B, like that you're getting. So now it is negative of, this you leave. Here you will get A times B square minus C square, plus B times is going to say A square, plus C times A square minus B square. And this is now this. So now what you will get? So now remember this example, sigma A square B minus C, sigma A square B minus C, that was A minus B, B minus C, C minus A negative. And if you get sigma A times B square minus C square, this is A minus B, B minus C, C minus A. Look for the coefficient of AB square, AB square, AB squared. So 1A and 2 B's. So 1A, so negative A, B and negative B, so plus. So this one will be plus only. No need to change, because it already is this one. So this is plus, right? So this is minus, and this is, you are getting plus thing, A minus B, B minus C, C minus A, upon A minus B, B minus C, C minus A. So this is C minus A. So this answer happens to be negative 1 and not 1. So this answer happens to be negative 1. This is negative 1. You can check that later. This happens to be negative 1. So in all of them now, what we are doing examples, they all have come in many contest problems, and they keep coming in many other problems also. So in all of them we are doing just one thing, that what we are doing is this, that we are taking the LCM in the denominator, and the numerator you are adjusting by sending things from here, and then we are simplifying that. That is the common theme running throughout. So this is what we are doing throughout. Then let's go to the next one. Next is this one, BCA plus D. Now, the moment you look at this problem, you understand that this has nothing to do with symbol D, right? The thing is working only on three symbols A, B, C. So I will separate it. So I'll write this as BCA over A minus B, A minus C, and plus BCD over this one BCD. If I separate three terms like this and this separate, if I separate them, let's see what we get. Are you getting my idea? That some hint you might have got the way I'm doing. We have done many problems. So BCA, normally I try that I give you the complete picture, and so I give you a lot of examples, at least 18 or 20. Okay, sometime mode also, or sometimes seconds and also, so that you can get adapted to all the ways of thinking, right? So it's like you can revise anything you want, and it's good for learning also, right? So you will write BCA and then BCA, then this is 1 by A minus B, A minus C, plus 1 by B minus C, B minus A, 1 by C minus A, C minus B, this one, and D. In D it is all common, right? So D is common, and you are getting BC upon A minus B, A minus C, and CA upon B minus C, B minus A, and all those numbers here. Now this is 0 because BCA, and when you get here A minus B, B minus C, C minus A, you are getting here A minus B plus B minus C plus C minus A, so 0. So this part is 0, this part is 0, and the other part will give you the answer, because plus D times sigma this one. So we need to find the numerator sigma BC. Numerator we want to find, that is sigma BC times B minus C, sigma BC times B minus C, and what will that become? Sigma BC times B minus C. So that will become like this, that we already have done this BC or AB minus B. So just check the sign. So we write sigma AB A minus B is A minus B, B minus C, C minus A. This sign will come as A squared B, right? A squared B, A squared B. So you can check here, A squared B means you want 2A and 1B. So you will get 1A from here, 1A from here, and B from here. So A squared B, you check A. So let me write this, rewrite once. So this is A minus B minus C minus A. So you will get 2A. So 2A is here and 1B here. So A squared B, this is negative sign. This is negative. Sign is negative. And so this also is negative. And so you will get here sigma BC D times this upon A minus B C, C minus N, this one. And so final answer is D. So you'll get D. Just simple answer is D. Good. We did not expect that we'll get D as the answer, but here it is. We got D as the answer. So that is good. This thing we got at least. Let me move on and build the momentum for the USAMO problem. We are almost there. So keep watching and check all the things. This also is a tricky example. A square B plus C, A plus B plus C, and all those things. Here you will learn how to play or how to do with this one. So first of all, that you will get here negative of, and you are getting A minus B, B minus C, C minus A, and here first you will get A square, A plus B, A plus C, and times B minus C, times B minus C, A square B minus C. Okay, let's look at it, that what we are getting. So I will just take this one, sigma A square. I will focus on sigma A square, A plus B, A plus C, B minus C. And for this to do, first I will expand this one. So without sigma, I will write A square, A plus B, A plus C. That I can write as A square times, or let me write full first. I want to develop A square, A plus B, A plus C times B minus C. So I want to do like this. I want to write A square times, this is A square plus b plus c times a plus bc times b minus c. This I get a squared and this. So I can deal in so many ways here. One way will be this, that one useful way will be that I can write this as a square, and this I can write as, I can take a as the common. So I'll take a as the common. If I take common, I'll get a plus b plus c and plus bc and times b minus c. This already is there. Or I can write a squared, and I can take just a squared here, and then this I can combine that ab plus bc plus ca, a squared plus ab plus bc plus ca and times b minus c. I can do like this. This is preferable. This is preferable. A cubed. This is preferable. A cube, a plus b plus c. So if I do this way, then if I have the first alternative, I got first and second alternative. First alternative, so I'll get a cubed times a plus b plus c, sigma I will write now, and this sigma is okay because this is a square bc b minus c. So I can write this as ABC is common, ABC, and sigma a times b minus c, which is, of course, this will go to 0. So I need not to worry about this. I need to worry about only this one, a cube plus b plus c. But this is nothing but a plus b, and this is b minus c, of course. So this will a plus b plus c is out, and sigma a cube b minus c. This we will get, this one, a cube b minus c. So we are getting a plus b plus c times a cube b minus c is a minus b, b minus c, c minus a, negative, and then you are getting a plus b plus c. This is cancelling, negative also is going. So finally I'm getting a good answer. I'm getting the answer as a plus b plus c whole squared. That's a really good answer, the whole squared. What about the other alternative? Had I taken this one, a square plus a, this also will work, but then we have some more thing to do here. But let us do it. Here we have stopped at a cube only, but here degrees increased. You will get a to the power 4. You will get a to the power 4, a to the 4. But then sometime people may not realize, so let me do that also. So now we are dealing with a square. Now we are dealing with a square times a times. So a square times a square plus. So a square times a squared plus ab bc ca and times b minus c. So this I will write as a to the 4 b minus c plus ab plus bc plus ca times a square b minus c. So if I write sigma of this one, a square plus ab plus bc plus ca times b minus c. So this equals sigma. Green is better. This equals sigma a to the 4 b minus c plus ab plus bc plus ca sigma a squared b minus c. Now sigma a to the 4 b minus c, that number is negative of a minus b, b minus c, c minus a, and times, you are getting here, this a4 is there, you will get here a squared, b squared, c squared plus ab plus bc plus ca. And then here you are getting here ab plus bc plus ca, that is alright, just you leave that one, a plus bc plus ca, and times a square b minus c. So that number is negative of, so that is negative of b minus c, c minus a minus b. So this is common, so negative of a minus b, b minus c, c minus a is common, and getting a square plus b square plus c square plus 2 times ab plus bc plus ca. This also gives you the answer in a nice way and tells you one identity. So minus a minus b, b minus c, c minus a times a plus b plus c whole squared. So this goes away from denominator, and so your answer still remains a plus b plus c whole square. That's good. So we still get the same answer. Is that clear? Any doubt here? Anyone wants to ask something? That how we got this? We got a plus b plus c whole squared. This is a tricky problem. This is like in many algebra text you will find that this really is awesome. So a plus b plus c whole squared. Let me go to the next one. A cubed b minus c plus b cubed c minus a plus c cubed a minus b upon this one. This should be easy, because now we know a lot of things. So can someone tell the answer for this one quickly? What we expect and what we get here? Almost you can do mentally. A cubed b minus c plus b cubed c minus a plus c cubed a minus b. Okay, we'll get this way. It is just a standard result, right? A cube b minus c, sigma a cube b minus c, we know by now this negative of a minus b, b minus c, c minus a times a plus b plus c. This we have done so many times. And now this one, this you might have forgotten. This I did know the lectures. This is this one, because the sum of these numbers is 0. It is x cubed plus y cubed plus g cubed. X plus y plus g 0. That is nothing but 3 times xyg. So this number becomes 3 times b minus c, c minus a minus b. So the expression p becomes negative of a minus b, b minus c, c minus a times a plus b plus c, and upon a minus b, b minus c, c minus a. And so your answer is negative of a plus b plus c by 3. So this is your answer, negative of this by 3. This is a good answer, but it is a simple problem. It's not so difficult. Earlier was much more. Okay. Next is this one, a squared. So the first thing to note here is that somebody may have the idea, somebody may think that we can take 1 by c and 1 by b, and we can work with those numbers. No, like we can work with, this is sigma xy and x minus y. That's fine. You can work with that also. X is 1 by c. But here we have to make a choice, because here we can't work now. Right? Here we cannot work now. We have to make a thing. So it depends on you how you think about it. I will offer you two things, two advice. One is this one, that let me work with 1 by a, 1 by 1 by c. If for that to happen, I will write this as I can take a square, b square, c square common. Okay, that is common. A square, b square, c square common. So a square, b square is common, and then I can write here 1 by b square, 1 by c square times 1 by c square minus 1 by b square plus 1 by a square, 1 by b square, then plus 1 by a square, c square rather, 1 by a square minus 1 by c squared, and plus 1 by a squared, b squared, 1 by b squared minus 1 by a squared. Like that we can get this one. And upon 1 by bc, 1 by c minus 1 by b, and all those numbers. So I can use this also. I can check that I can take 1 by a, I can take 1 by a as x, 1 by b is y, 1 by c is z, and I can apply here this result, right? This is also one way. This is also one way. So that we can write here as this is 1 by bc. So I can write here 1. This is yg and y minus g plus gx g minus x just take care of signs. So this is yg, y minus g, plus I can write here gx and x minus g and xy and y minus x. It is like this, and same thing goes here. So this I can factorize. This I can factorize in terms of x minus y, y minus g, g minus x, and here I can apply to x square, y square, g square here. That will be simple. That will quickly come. So that is one aspect of it. Other aspect is this. That also is nice, that you clear the denominator in the beginning only. So what you write here, that this you write as a squared times b square minus c square. B square, c square gone. This one. So you will get here a to the 4. You will get here a to the 4. So you will get a to the 4 b square minus c square plus b to the 4 c square minus a square plus c to the 4 a square minus b square. This one, and you are writing a square, b square, c square. So you will get here times 1 by a square, b square, c square. Here you can again take the denominators. So I'll get 1 by a square, b square, c square, and here you can write bc goes up, right? Bc goes up here, so that becomes bc, b minus c. So you get bc, b minus c, plus ca, c minus a, plus ab, a minus b. Just check that this you are getting. You are getting this kind of thing, right? Or you are getting a square. No, you are getting a square, not this. You are getting a square. You are getting a square, b minus c. You are getting a square, because this is a square, b square, c square. So you are getting a square, b minus c, plus b square, c minus a, c square, a minus b. Apply the same result. This is gone. This will become a square minus b square minus c square minus a square, negative of that. This will become negative of a minus b. Don't leave negative, c minus a. And so negative gone. And now we are getting simple result a plus b, b plus c, c plus a, plus, all plus. So good result, really good result. A plus c, b plus c, c plus a. So this is also one good result that you get. Okay. What about this one? This is easy. A cube b minus c, almost automatic. Almost automatic. You can do that easily. And I can just tell you the answer for that. So that will be a plus b plus c. Just apply sigma a cubed b minus c. This you know what it is. And you also know what is sigma a squared b minus c. That should be enough to give the result. This, both of them. This is one tough problem, and this is okay, and then we will get to the USAMO problem. So this problem I'll just give you the hint that how you will complete. So this is a squared b minus c cubed. We have to deal with sigma a squared b minus c cubed. So sigma I will write later. First let me write a squared b minus c cubed. So this I can write as a square n times b cubed minus c cubed minus 3bc b minus c. This we get this way. If you write sigma, so sigma a square b minus c cubed is sigma a squared b cubed minus c cubed minus 3bc b minus c. You will get here sigma a squared b cube minus c cube is alright. Next only minus of 3, and I can take abc out. So I can take abc out because that will permute. So minus 3 times abc is out, and sigma a times b minus c, and that will give you 0. This will give you 0. This will give you 0. So ultimately you are left to deal with sigma a square b cubed minus c cubed. This is a tough problem. Very, very tough, challenging. Now, how do you deal with this one? you can go back to basics and you can again try to write other things, but better would be this, that you write here sigma a square, again you write b minus c and b square plus bc plus c square. Sigma a squared b minus c b square plus c square, and plus sigma, see this is again a different thing, right? Sigma a square bc, so we can again write sigma a square bc just like last term. You will get plus abc sigma a times b minus c. This will be again 0 on 3 symbols, so it is again 0. So this thing again goes to 0, this thing again goes to 0. But now we are almost there, so we got sigma a square b minus c b squared plus c squared, not minus, plus c squared plus. So how do you play with this one? This is like this. Now it is sigma a squared b minus c b squared plus c squared. I do a nice trick. I write sigma a square b minus c. I write a square plus b square plus c square minus a square. So I will write sigma a square b square c square times a square b minus c minus sigma a to the 4 b minus c. This I write. Now almost it is done, this one, because this is now a square plus b square plus c square is common. This is sigma a square b minus c minus sigma a to the power 4 b minus c. I know this is common. This whole thing is common here. This is always a part of it, right? A to the power 4. So I can take common. I can write sigma a square times b minus c times a square plus b square plus c square, and minus, after this common, what we are left with is this a square b minus c. So we are left with the second term. We will get a square plus b square plus c square plus ab plus bc plus ca. And so I am getting here negative of ab plus bc plus ca sigma a square b minus c. And we already have this also. If you check it, you already have this one, a minus c minus c minus a squared, correct? And so you can take care of this, and then this will be negative. Negative will come up from here, and so it will be positive. And already we have got in the denominator, we have got again same a minus b minus c minus a. So your final answer will be ab plus bc plus ca. This is your final answer, ab plus bc plus ca. That's good enough. Let's go to this one, 1 by a b minus c, and this one 1 by a. Here again, better that I can just write out the whole thing. So what I'll do here, that we'll take ABC as this one, ABC as the LCM. So we'll get here BC B minus C. We'll get BC B minus C sigma. ABC will be out. So here you have got ABC. That ABC will cancel or no. So I'll just write ABC. And here I will write here you have got A squared, B squared, C squared. That will come. And so B squared, this is C squared minus B squared. So I will write C squared minus B squared C squared, and A is there, so you will get here A. So A times this plus B times A squared minus C squared plus C times B squared minus A squared. This you are getting. And so this ultimately you will get easy, because this you will just get ABC. Why? Because ABC will be here. This is 1 by ABC, and this is this. You will get ABC, and this thing, they both match. They both match because this is sign also matches. This is negative of sigma A B square minus C square. So that equals now this one. So you will get this as ABC. Now let's come to the attraction that this is the USAMO problem. This is your USAMO 2014 problem, because see the year is saying 2014. Just check it out later. So this solution goes like this. This solution, see, they are saying that exists an infinite set of points in the plane with the following property: for any three distinct integers a and b with points pa, pb, pc are collinear if and only if. Now how are the points collinear? Points collinear means that certain determinants are 0, right? If points are collinear, then certain determinant is 0. So what I do, I will choose here something. Let me choose here something. This determinant is 0. What we can choose, which relates to this chapter. See, a plus b plus c is 2000. See, if you do the factorization of sigma a square b minus c, sigma a cubed b minus c, sigma a to the 4 b minus c, anything you do, one factor that comes out is always a minus b, b minus c, c minus a. What about the other ones? So in other ones, you remember that this had a factor a plus b plus c. This factor was not useful. This factor is a squared b squared c squared plus ab plus bc plus ca. This was this factor. It is afford. AQ factor is most interesting. A plus b plus c. But if I take this, suppose I take determinant like this. Suppose I take a determinant here such that it has a cubed a1, b cubed b1, and c cubed c1. If I take this one, a cubed, this one. So this determinant is how much? This is actually, if you sum, this is a cubed b minus c. So this is sigma a cubed b minus c, which becomes a minus b, b minus c, c minus a, and times a plus b plus c. But if I do this one, then you will get not 0, you will get some 20, 14 or something you will get, right? We want to be collinear, we want it to make 0, but this is 2014. So how do you get rid of that? How do you attack that so that you get just what you need, like what the doctor ordered? So can we tweak it a little bit? Can we tweak our choice of A, B and C a little bit, just that we just get the right ingredient? Can you think of it? Can you think fast that how we will get? See, the trick lies here that I can change A, this ABC is there, right? I want to preserve this difference because I want them to be distinct, pointers distinct. So what I can do? Is there some response from the viewers? Then I may wait for a moment so that they can say something about it. Okay, so what we can do is this, that if I replace A, write this as 3 alpha means alpha will be 2014 by 3. It does not matter if it is not a lattice point because they never said lattice points. Just A must be integers, right? ABC. 3 alpha of course need not be. Now, so if I replace A with A plus alpha, B with B plus alpha, or A minus alpha, if I replace A with A minus alpha and C with C minus alpha, this one, if I replace like this, where 3 alpha is 2 and 4, then what will happen? That if I take the same determinant, means I take A minus alpha cubed, A minus alpha 1 and 3 such things, then I get negative of, this does not change, this is just A minus B, this does not change, but here it is changing. Here you are getting A plus B plus C minus 3 alpha, so that we have now got the point that 2014, and so from there we can prove that it must be true. We have got the rough idea of the proof. Let's write it now. We have already got the rough idea of the proof. Let's write it now. So writing part will look like this, that so we will define that let us take PA as A minus 2014 by 3 cubed and A minus 204 by 3, PB B minus 2014 by 3 cubed, B minus 204 by 3, and PC C minus 2014 by 3 cubed by 3. If you take like this, then that's good enough, no? Because they are infinite number, because they are saying that infinite with points, no, for any 3 distinct points integers, so exists this point in the plane with the following property: for any 3 distinct integers a, b and c, the points p, p, c are collinear if and only if this is 2014, if and only if this is collinear if and only if. So we are getting this point. So we were successfully getting, no, PA is A minus this one, PB, ABC are integers. So we are getting 3 distinct points, and the area of triangle formed by 3 points is half. And so if determinant, so in determinant language, that is this determinant, which I am calling A minus alpha cubed, B minus alpha cubed, C minus alpha cubed, and this is A minus alpha, B minus alpha, C minus alpha, 1 1 1, A minus alpha, B minus alpha, A minus alpha, B minus alpha, C minus alpha, C minus alpha. We are getting C minus alpha cubed and C minus alpha. So this determinant when you evaluate, this will become A minus B, B minus C, C minus A, because difference is same. So we will get this times C minus A negative, and you will get A plus B plus C minus 3 alpha. And so this is 2014, so this will be 0. So you will get that for these things, this all are 0, and this one, and the points are distinct. So collinear if and only if, right? Points are distinct, right? So these are of course not 0, they are distinct points, because A is not B is not C. But then this is 0. This is 0. We have ensured like that. We can take ABC different always. So this is distinct, and so this ensured this is 0, and so this delta is 0, and delta is 0 if and only if the points PB, PA, PB, PC are collinear. This only when these are collinear, and we will get the result collinear. So is that clear? Did you get that easily? That how it is coming? It was a challenging problem in USAMO 2014. Statistics was not good about this problem. People might not have thought about this one, because this is actually the motivation is coming from this kind of coming up with some kind of identity which ensures that the factor is A plus E plus C. That was the motivation, that the factor is A plus B plus C minus 2014. That must be the factor, and if that is the factor, then of course you will have to do that kind of thing. So is that clear? So just to give you a quick review, that what we did today what I achieved was this, that I told you in the beginning some identities that are at the heart of today's chapter. So we have these 4 identities. Yes, these are all proofs. So we have this one, means today we did something like sigma a to the m b minus c. How to deal with this one? This is what we have done. Sigma a to the m b minus c, and this we are doing. So I hope that the recurrence proof also was clear, as also the other proof.